Okay, so we've learnt about extensional strains, we've learnt about volumetric strains and their rate of change. The last thing that we really need to think about is the idea of what people would call the rate of shearing strain, or to truncate that, to keep it simple, people will often just refer to a shear rate. Some of you may have seen this before, and frequently, if you've seen it before, you will have called gamma a shear strain, and so since we're interested in the rate of it, you might well have seen it written with a dot over it, and so this would be frequently called gamma dot, and it would have units, again, of inverse seconds. And that's what we want to try and understand today. So let's imagine our little material element that we have right here, and we've thought about the idea that it might move through space, it might get stretched, it might get expanded, but the final thing that we might be interested in is that the orientation of these angles of these material lines might also be changed. And so if this is what a material element looks like, if we draw a pair of axes in here at time t, at a time t plus dt, we might find that in addition, that the material point here has moved to a new angle that we might call b primed, and we'll denote the angle of that change as d beta. Similarly, this material point here might also have moved or might be rotated, and so we might also be interested in that it might have gone to a point d primed, and this angle we'll refer to as d alpha. And so what a shearing strain measures is indeed the change or the change in orientation of a material element like that. So if I have a material element that's square, we know that it can be translated through space, we know it can be rotated through space, but what we're thinking about now is that the angle of the material elements may themselves be changed. And so this material element may be getting stretched and deformed into something very non-square. And that's what we're going to try and evaluate. So what we'd like to do is we'd like to find an expression for d alpha. And so d alpha is the change in the angle. And we're going to think about an infinitesimally small time. So this would be after a time dt later. And so when the angles are small, we're going to make the approximation that tan of d alpha is about the same as d alpha. So for very, very small angles, we might remember that the expansion of sine and tan of x is that they're just the values themselves. So what we want to do is we want to evaluate that, and the tan of this is going to be telling us about the size d primed divided by the original size of this material element, which as we've seen here is del x2, and this is of size del x1. So we're going to use the same idea that we had before, that we might know the velocity at point D, but we are also interested in comparing the idea that point A moves through space and point D also moves through space. And the velocity that we're interested in here may be different than the velocity at the point right here. And so the angle that we're going to be interested in, d alpha, would be equal to the distance d primed, so the line element d to d primed, divided by the initial length of this line element, which is del x2, and so that's calculating the tan of this angle. So what we need to do is we need to find the change in this length, and so if we think about point D will be moving through space at a velocity that's different than point A is moving through space. So if this is point A, and this is point D, our initial line is there. At the next instant in time, then D has moved to D primed, and A has moved to A primed. This first one is very easy for us to evaluate. This would just be V1 times the time distance del t. But we need to evaluate the same thing for this distance here. And so now this is not V1, because this point is moving at a different speed, but it would be V1 plus a variation in the distance. But this is now varying over distance del x2. So we would write this as dv1 by dx2 times the step size dx2. And so this would be the velocity of this material point here. The distance traveled will then just be that multiplied by time. So that gives me the distance that has traveled. And so now we can compare these two, and that will give us the difference in these two. So we can say that it's this quantity, V1 plus dV1 by dx2 times our step size del x2 times this time dt minus this length, so that we're just going to be calculating this extra little bit right here. And so this would be V1 times del t. And then we'll divide that by our original distance del x2. And that will give us an expression that will indeed look like, we can see that these terms cancel. This will cancel with this, and so I'm left with dv1 by dx2 times the time step over which this happens, which is delta t. And so since we're interested in the rate of change, the final thing we might evaluate is we might evaluate d alpha by dt by taking the limit for del t goes to 0. And then indeed we just get that this is equal to dv1 by dx2. And so we now have an expression for the rate of change of angle alpha. And we can evaluate the same thing for d beta by dt. So we might like to evaluate that. And the only difference here is that we have to think now about the idea that these 2 points are moving through space, and they're not moving at a constant velocity. They're actually changing. And so now we need to know that it's this velocity that we're interested in here is now in the 2 direction, and its variations in the 1 direction. And so everything will be the same as this. We'll just end up that this will be the variation in V2 with a step size that's in the x direction. So in fact, we'll end up that this will be dv2 by dx1. And so both of those things may be changing as a function of time. And so people will then choose to express the rate of strain in terms of either the total rate of change of this or maybe in terms of the average of this. And so we'll see that people will sometimes use the total rate of change following our material element. And so they might express that as dv1 by dx2 plus dv2 by dx1. And that they would typically write as gamma dot. And then since we're interested in elements in the 1-2 plane, we'll recognize that that is gamma dot 1-2. Now, other people will choose not to say the total rate of change. They might say, well, I've got these 2 angles, and let me calculate the average in this. And so sometimes people will also write the average. And so we could write that as 1/2 gamma dot 1-2. And that would be frequently called epsilon dot 1-2. And of course, that will just be equal to 1/2 of grad V1 by. And different books will use different notations, and so you just have to be a little bit careful to see which way they're doing it. But the key idea that we've got now is that we can now think about our deformation of our material element, and we've written down all of the different ways that things can deform. We have a translation, we have a rotation, we have stretching, and we also have shearing. And in the next page, we'll just summarize all of those different modes together.